Hello, and welcome to Lecture 15 of AMAT502 at UAlbany. Today, we're going to do a brief recap on some of the topics from regression and classification that we did in the previous two lectures. This will allow us to go a little more into depth of both the coding aspects of simple examples in these two machine learning methods, as well as a way of developing the some of mathematical awareness behind what can go wrong in each of these methods. Finally, we'll conclude the lecture with a fairly straightforward introduction to some of the syntax behind pandas. Pandas data frames are going to be one of the main objects which we use when we start using more and more machine learning techniques. So let's do a quick recap on supervised learning. So remember, supervised learning is all about labeled data. So you're assuming that someone is giving you some training data where that data already comes with labels. There's sort of two types of labels that you can look at. On one hand, you have sort of numerical labels, things like height or weight or income or maybe a gene expression level. In these situations, we tend to use regression. On the other hand, if we're looking at categorical variables, so things like democratic republic, rents or owns, mammal or bird, we want to use something that is called classification. So those are the main two branches of supervised learning. So I want to give you a little more insight into how things actually work under the hood when doing regression in Python. So as a quick reminder, when we talk about linear regression, what we're trying to do is, imagine we're given a collection of XY pairs. So these are points that are labeled inside of, or points that are in two dimensions. In linear regression, we're interested in trying to find a line that best fits our data, best predicts Y as a response variable to X. By nature of it being a linear model, we use the equation y equals mx plus b, where of course m here refers to the slope and b refers to the y-intercept. Now, additionally, we could imagine that x, our independent variable, the one that y depends on, has lots of variables. So meaning it's not just one scalar of quantity x, but rather a whole vector of scalar quantities, x1 through xn. So in this setting, you can also phrase what you might call a multi-dimensional linear regression problem by saying, well, I predict that y responds to x as some constant, beta 0, plus a whole vector of betas, beta 1 through beta n, that when I take the dot product with x viewed as a vector, this is the thing which sort of best fits my data. In this case, you want to imagine, again, you've got your points lying in some sort of n-dimensional space, and you're trying to fit some sort of hyperplane to that data. Now, under the hood, Python likes to turn polynomial regression problems, so meaning where we don't just have a linear coefficient like this, into a multidimensional linear regression problem. Now, how does this work? So typically what this means is that even if you've got just regression in one variable, so you have a single x scalar value and you have some responding value y, you can always apply the following transformation, which effectively takes x and then considers higher powers of it and stores each of those higher powers in the coefficients in a vector. So this means I could take a function of one variable, just single x, and turn it into a vector of length n. And so now if I do multidimensional linear regression on not just x, but phi of x, which is the process of transforming x into this column vector where I have x squared, xn. And if I look at the dot product of beta, suddenly this looks like a polynomial regression problem. And so this is partly done because Python was written with the intention that you're going to be working with multidimensional data. Linear regression is the most useful one in that setting. But as a bonus, you can actually do polynomial regression via linear regression after you've applied this transformation. And I'll try to point out in the code where that happens. All right, so in the live exercises, which are generally not recorded and occur in my live class sessions, we considered a problem of how do we predict the next number in an integer sequence? Of course, I alluded to that in lecture 13. And I had baked in there actually an example that was very similar to the Fibonacci numbers. And so in this live lecture, we went ahead and tried to understand, could we fit a polynomial to the Fibonacci numbers? So let's try to do that here. And I'll try to point out some of the problems along the way. So as a recap, remember that Fibonacci numbers are those numbers which satisfy this following recurrence relation or recursion relation, meaning I take the previous two Fibonacci numbers, I add them together, and that gives me the next one. When I take the seed values of f0 equals 1 and f1 equals 1, that leads to the really traditional progression for the Fibonacci numbers. So let's ask, how could we maybe try to model these Fibonacci numbers if we weren't able to figure out this pattern, that namely the nth Fibonacci number is the sum of the previous two. So in our trained model predict paradigm, we're going to imagine we have some sample observations. This is our perceiving of data. And in this case, what we're going to look at is the first 20 Fibonacci numbers. We're going to go ahead and choose a model which says that I believe the Fibonacci numbers behave according to some polynomial. And as I already wrote, I can think of this as some beta 0 up through beta n to the xn. And now I'm going to evaluate, while my model is off, I'm going to use this sort of sum of squared residuals or sum of squared errors to then try to pick my ideal choice of my beta coefficients for that fixed degree n. But I'm also going to play around with changing n. So those are kind of all hyperparameters in the model of polynomial regression. And I'm going to try to be conscientious of overfitting and underfitting. All this is going to lead me to try to understand, can I predict what the 21st Fibonacci number is? So I'm assuming, again, I haven't figured out that recursion relation. I'm just going to use polynomial regression to try to do that. All right, so let's get into it. So first, I've got my usual function for defining the Fibonacci numbers. I'm just using this to generate my synthetic data. And of course, I'm using here a classic recursive algorithm or code for the nth Fibonacci number. And then I'm going to look at FibList, where I use list comprehension to go ahead and populate a list of the first n Fibonacci numbers. And so my data is going to look something like this. Generally speaking, when we work with any of these scikit-learn packages, it really prefers that we have column data. Now, columns in sort of list form is just a long list of lists where each list entry is just a list of length 1. Notice that when I print y, it actually assumes this sort of column vector notation. This is just a convention, but again, it's something that you have to be mindful of, and often you'll need to reshape your data so that it looks like this. So what's going on here? We have x is just the integers from 0 to 19. And so now I'm looking at the 0th Fibonacci number up through the 19th Fibonacci number. Again, shifting everything down in 1 because that's how Python likes to work. And so this is my independent variable, the index. My dependent variable is my nth Fibonacci number. All right, so just sort of reading through this code briefly, you can see here that I've got NumPy, I'm going to bring in as NP, my matplotlib.pyplot as plot, pandas as PD, and that's we're going to explain more carefully. We're not actually going to use pandas in this particular example, but so in sklearn, we have a linear model, which we use with linear regression, and then we also do what's called pre-processing. This is exactly that step I mentioned where I apply this function phi, which turns x into a vector of x1, x2, x3, x4, where each of those entries is really x, x squared, x cubed, x to the 4th. Right, so let's maybe start a little bit lower, and let's imagine I'm doing a degree 4 polynomial. So that's going to be my polyreg object. It's polynomial features, degree 4. This is sort of doing my pre-processing. So x, again, you remember, is just this list of lists, which you want to think of as a column vector. The integers 0 through 19. And so it's going to provide some sort of transform on this poly-reg. And what's happening is exactly what I said in that phi function does, is it takes x, it looks at that power squared and cubed and so on and so forth. That's what's happening right here in this x poly. And notice that once I've done that, I'm essentially now providing my linear regression problem with a whole vector where each of those entries is populated with one of those coordinates raised to the first or second or third or fourth power. So I create a linear regression object. And again, the paradigm you need to have here, or the mindset you need to have here, is that we're using object-oriented programming. I can update attributes of these objects by passing it in corresponding data. And it has under the hood written algorithms for how to provide these fits. So what do I do? So I have my x poly, it's my poly-reg object. And then I've also got poly-reg. And now I'm going to fit my linear regression object using my transformed data. This is the integers 0 through 19, which have been then turned into a matrix where I've got 1, 2, and third, and up all the way up to the now fourth power. And I'm going to try to fit that using these values and try to find out what's a good line that fits this. And so all this is now just an auxiliary function for just plotting and viewing what's going on here. So let's go ahead and see what happens. All right, so again, didn't actually plot it the first time through, but hitting Shift Enter twice, I now see that I've got this quartic, that's what degree 4 means, quartic polynomial, which seems to be trending fairly close to my Fibonacci numbers, the first 20 Fibonacci numbers. But I've gone ahead and written some print statements, which goes through and actually looks at, well, how do I predict values? So notice I can predict values using this polyreg.predict. So my polreg, which is was my linear regression object, but now with the understanding it's happening under the scenes as a sort of multi-dimensional regression problem applied to this transformation, this phi of x that I just introduced. And so I'm going to go ahead and extract that out as ypred. You'll notice this is what was plotted. I had x comma polyreg of fit transform of x, where I've then applied the predict number. And so what I could do here is, because both of these things are NumPy arrays in essence, I can look at all my predicted y values. I can look at the actual y values, which again stores in the Fibonacci numbers, index from 0 to 19. And it knows to take component by component, square it and square that. And then here what I can do is then actually take that difference, square it, and then I can sum up all of those. And this is effectively my sum of squares error. And then if I want to predict, well, what is my polynomial regression model predict? Notice I have this dot predict method being called on 21. So that's our 20th or 21st number. You can see that it is still off by quite a bit. So our prediction of the next Fibonacci number is something like 12,908. The actual next Fibonacci number, 21st, is 17,711. Then you can see that that error is quite large. Now let's go ahead and just tune some of these parameters in the model. So instead of like a degree 4 polynomial, let's try to do a degree 6. Like you see, visually it looks a lot better, but in its prediction is getting closer, 16,000 versus 17,000, but still off by 1,300. And our sum square errors is still 3,258. And so we can go higher still. We could say, what about 10? So 10 actually gets very, very close to predicting almost exactly all these Fibonacci numbers. Indeed, it gives us 17,672, 17,711 was the actual one, off only by 38. But now we're getting into a situation where our degree of our polynomial is actually pretty close to the number of samples we're having. We gave 20 samples. That means we have like 20 points. And if you remember, we had these Lagrange polynomials, which, you know, actually, if we end up giving this a full degree 20 polynomial, well, in this case, it actually, it's off quite a bit. But I think that's something else that's going on here. But let's just say that maybe degree 12, sort of our sweet spot right there. Here we're in a situation where we're practically overfitting. But now let's go ahead and just think about, luckily we know something about the Fibonacci numbers. We can ask, was this model actually a reasonable one to use? And I'll contend that it's not. And here's sort of a back of the envelope calculation as to why it's not a good model. So again, our model is that this sequence of numbers is modeled using some polynomial. But if we have a little more subject matter expertise, we could see that, well, it's actually well known that the ratio of the Fibonacci numbers, of the nth plus 1 Fibonacci number to the nth Fibonacci number, if I take the limit as that goes to infinity, approaches this very, very famous number called phi, which is the golden ratio. 1 plus the square root of 5 divided by 2. Now, let's just play around a little bit here. If we know that the ratio of these Fibonacci numbers is going as basically the golden ratio, I can use this to try to figure out what kind of like a discrete derivative is for this function, which is modeling the Fibonacci numbers. So let's call that dfn. And we'll just do it as you would normally do in calculus. You take f of x plus some step size minus f of x divided by the step size. In this case, it's f of n plus 1 minus f of n divided by n plus 1 minus n. Now, of course, n plus 1 minus n, it's just going to leave us with 1 in the denominator, so I don't even need to do that. And if I use this approximation that increasingly the next Fibonacci number is given by just taking the previous one and multiplying by phi, then I get this sort of approximation for the discrete derivative. But if I, again, just sort of, calculate this out and I see that, well, phi is greater than 1, it's in fact 1.618. What I see here is that my discrete derivative depends on my function value. And if you think back to calculus, what happens when we have like the derivative of y viewed as a function of x is proportional to some constant times y. That usually means that you're in a setting of exponential growth. And exponentials are by definition not polynomial. In fact, they require the whole infinite sequence of terms in order to express an exponential. But we can even be a little more precise. So in fact, there is a closed form formula for the Fibonacci numbers, which says that the nth Fibonacci number goes as phi to the n, again, where phi is the golden ratio here, and then minus, some correction factor. So all this is to say that no single degree n polynomial is going to do the trick for predicting all the Fibonacci numbers. Even if I somehow fit my data very well for, say, 20 observations, if I were to then have like another 10, would have been even farther off. So all this is to say, you can't always use a model like polynomials for doing regression on data, but more often than not, you can. All right, so let's then recap. So that was just sort of some of the material from lecture 13, where we introduced machine learning and we gave regression as a method of learning what a number sequence, how it behaves. It can be something that's treated using machine learning, specifically regression. Our last lecture, where we got into sort of morphology and how do we like classify animals, that motivated two examples of classification algorithms. There's sort of a linear classifier, and then there's also what's called the k-nearest neighbor classifier. So let's go ahead and like get into how this linear classifier works. The setting that we were interested in was in the setting where we only had two class labels, red and blue. And the model was that there was some hyperplane or a line in dimension 2 that separates red points from blue points. I kind of skimmed over what was the training and the penalty function there, but if you learn or read a little bit more, you'll see that what we're trying to do is we're trying to maximize the distance from the nearest red point and the nearest blue point from that line or from that hyperplane. We do a longer lecture on support vector machines. I'll get into that. But anyhow, once we've developed or picked such a hyperplane, the way we predict what a test sample is going to be is then we ask what side of the hyperplane does it lie on. And that can be expressed by taking the dot product with the normal vector and then seeing is that positive or negative. And then we can compare that. That positive or negative is often compared with some sort of displacement d. All right, so again, let's try to go through, and here I've given you sort of a more simple, contrived data set where I've gone ahead and hand positioned some red points and some blue points. And I want you to think of these gray points as sort of our test samples, which we're going to try to figure out. According to our linear classifier, what would we predict these gray points as? We need to reveal their true colors. Are they red or are they blue? So how is this all expressed in the computer? So in this case, you could think of, we've got our training data as a collection of XY pairs, which I'm expressing again as a list of lists, but this time it's you want to think of it as two column vectors where I have all of my X values, all my Y values, but then I'm also interested in this Y train, which are these sort of Z values. That's a class label value. And in this setting, we can plot it very easily, just as is indicated here. But I've gone ahead and create a little color dictionary for determining, depending on whether my Y value is, if it's 0, I'm going to think that's red. And if for 1, I'm going to think of that as blue. So here now my class labels, they're technically numerical, but I'm just using that as a trick because ultimately everything in a computer is represented using a number. I still want to think of these as categorical variables, not ones we're regressing on. Okay, so the code for using a linear classifier in Python is part of this SVM, support vector machines library. And here we look at SVC, support vector classifier. I'll explain in a later lecture what this kernel means, but linear is the thing that makes this a linear classifier. So let's go ahead and fit. So again, we create an SVC object. So support vector classifier object. And then I'm going to apply my fit method with my training data. And if you just remember here, X train is this 1.75, comma 1.2, something like this. 1.75, comma 1.2, so there's 1.2. This is supposed to be 1.75 as the X value. Here I have 2.5, comma 0. All right, so I've hand coded all of these red points in here. And this is my training, this is my features, and then this is my response, my class label. All right, so again, got that, and now I'm going to apply my fit method here. So all this does is it just tells me that I created an object and did all this stuff. How would I actually predict what these values are? So what ends up happening is that it creates what's called a decision function where, I've got these two values, 0 and 1, and I'm thinking of if my test function is negative, then that tells me it's going to be part of my 0 class. And if it's positive, I'm thinking that's part of my 1 class. So let's see what happens when I do this. Okay, so when I call this on my test data, those are my 3 gray points. The first one gets a negative decision function value. Next one's positive, and the next one's even more positive. If I interpret that, that means this is supposed to be red. These are the ones where I have the class label 0. And these two are blue, where my class label is 1. But this also kind of expresses the confidence, meaning how far away from 0 it expresses how confident this classifier is in its predictions. And indeed, this actually looks right. You know, here, my test, if you go back and you look, this is my test points, X test. I didn't even give it values, but 3.5 comma 1, this is one. 3.95 comma 1.5, it's that guy. The next one's very close to X value 4, Y value 2, it's that guy. So it thinks that this point is red and these 2 points are blue, which seems pretty reasonable. All right, but let's see how we would actually judge that. And one thing we're going to do here is we're actually going to plot the decision boundary. So I encourage you to avail yourself of these sort of internet resources like Stack Overflow. And here they gave an answer of how to extract this line that is giving me the linear classifier. And it says that you can extract this using these publicly available attributes inside of my classifier object. It has a coefficient and it has an intercept. And you can extract the equation for y equals ax plus b using essentially this. So notice here, all I did was then create some x points, and then I applied my decision boundary to then graph this line. So this is the line that separates my red points and my blue points. All these were, again, just sort of attributes built into training my classifier using the scikit-learn API. So let's just do a quick recap. We'll get into this more later, but bottom line is not always is data linearly separable. And these sort of contrived examples, they are, and sometimes they are indeed. And as we get into our SVM lecture later in the semester, we'll see that these examples only worked well with two class labels, red and blue, 0 or 1. So we had the single hyperplane, but in general, we need more and more hyperplanes with the more class labels there were. All right, so let's look at our case study in our next classifier. This is the k-nearest neighbors algorithm. And so here our model is that the way in which we should predict class labels is that we take a test sample, we give it a parameter k, capital K, I call it little k here. And that k is some integer, 1, 2, 3. And then I look at what are my k closest points to me, my test sample. And again, I'm using the metric structure of the feature space that I'm in. And then I just go amongst those k closest points. I look at their class labels. Is it red or is it blue or is it orange? And I just count up, and I just use the rule majority wins. And that is how I predict class labels here. So if we go through and you look at exactly those red and blue points I just showed you, now I'm going to go ahead and create an instance of my KN neighbors classifier object. I'm just going to call this classifier. Again, I'm calling it a k-nearest neighbors classifier. I'm saying I'm going to look at my 3 closest neighbors. And so if I do that, and I go ahead and apply this to train on my X train and Y train, and notice it gives me all sorts of things like what metric it's using. It says Minkowski metric, which means it's of an LP metric, little LP, p equals 2. That means we're using actually the Euclidean distance here. It's great. Number of neighbors is 3, so it knows I did everything right. And then let's go ahead and predict for those 3 gray points what we get. And again, that's still stored in X test. So 0, 1, 1. So I gave it that 0 is red and then blue is 1. And it predicted again that that first point that's lowest and closest to the red cluster is red, and that the next 2 blue points are actually blue, or 2 gray points are blue. So in this case, actually KNN and my linear classifier issued the same prediction, which is good because I crafted the example by hand to make it look a little dubious, but to make it sort of clear that 1 should definitely be red and those 2 are probably blue. All right, so this is just to show you how you run the bare bones code of a k-nearest neighbors classifier. let's get into some of the drawbacks of KNN. So the first thing is you can try multiple values of K, but if you let K be too large, for example, in particular, if you let K be larger than the number of points in your sample or your training data set, then all it's going to say is which class is most popular overall. It's not going to use my proximity, because if K asks for what's my 1,000 closest neighbors and there's only 100 points, it's just going to look at all my neighbors and it's just going to do a general majority of rules. This is an example of how KNN can forget geometry. And again, that's not the point of KNN. KNN is supposed to use geometry to predict. And this is also tied into another problem, which, it's very important as aspiring data scientists that you know about. And this is the issue of the cursive dimensionality. And the cursive dimensionality is essentially the statement that as we let our feature vectors go into higher and higher dimensions, and these last two examples, everything was two-dimensional. But if we go higher, 3, 4, 5, 6, 7, 8, even higher, increasingly points are going to look equidistant from one another, which just means that it's going to be harder and harder to use geometry to try to separate out structure and data. So let's try to understand why that is. Why is it that things look increasingly the same distance from one another? So first, a little math notation. So when I'm talking in the n ball of radius r, this means let me look at a ball in our Rn Euclidean vector space. It's an n-dimensional vector space. And I just use the formula where I say, I'm going to take points that are within distance r of the origin. That's expressed using this. So here I'm doing the L2 in calcimetric, which means I essentially apply the Pythagorean theorem. I look at x1 squared plus x2 squared all the way up through xn squared, and I take the square root of that. Or I could just say, take the sum of those squares, ask if that's less than r. And that is going to be the definition, the math definition of the ball in higher dimensions. So let's try to understand this in some more specific settings. And in particular, let's think about what would it mean to talk about volume in each of these settings. So again, some terminology. When we say the unit n ball, we look at where r is equal to 1. And if you think about this definition, in the case where, let's say, n equals 1, that means we have a single vector. And then in that case, I just take the absolute value squared, and I'm asking if that's less than 1. Well, if you think about it, here's the origin. That means I can go up to -1 to the left or 1 to the right. And so the volume of the n ball for n equals 1, the unit n ball, is 2. In this case, volume is actually length, as we like to think of it. In dimension 2, so n equals 2, the volume corresponds with area. And you all know the famous formula for area that's inside a circle. It's pi r squared. So if I plug in r equals 1, that means that the area of the ball in dimension 2 is pi. And then what happens in n equals 3? Well, here I need to use the volume, and I can think of volume in the normal sense, the colloquial sense. It's 4 pi r cubed divided by 3. Again, you plug in r equals 1. That means the volume is 4 pi divided by 3. And notice that 4/3 is greater than 1. So there's more volume in dimension 3 than there is in dimension 2. And since pi is 3.14159 and so on, we know that there's more volume in dimension 2 than there is in dimension 1. And luckily, mathematicians have come up with formulas that go ahead and give me a precise expression for the volume of the n ball as a function of the radius, that's r to the n, and as a function of pi, which depends on n, as a function of n, which is the dimension. Now this gamma expression down here, maybe you haven't seen it before, but this is another way of trying to connect the dots in the factorial function. And that's what's called the gamma function. It shows up in a lot of places in math, including probability theory. Anyhow, just studying this pattern, you see that, okay, there's less volume in dimension 1 than there is in dimension 2. And there's more volume in dimension 3 than there is in dimension 2. Do you think this is just going to keep going up? Meaning as I go to higher and higher dimensions, there's more and more volume to be had. Well, let's go ahead and plot this function and just see what it looks like. So that's what I did here. I'm going to import my math library. Notice it's got a built-in gamma function. I wrote this little function, volume of the hypersphere. We'll give it radius and dimension. And so I'm going to go ahead and look at this NumPy array. It ranges between 1 and 20. I'm going to look at the volume of the hypersphere with radius 1, so red, I'm going to put to be 1, and then for I in dimension. And then I'm also going to do it for one where I've increased the radius slightly from 1 to 1.1, just to sort of see how that behaves. Let's go ahead and plot these guys. So this is pretty surprising. Again, if we look at this first function, it chooses, matplotlib chooses it to be blue. This corresponds to the volume of the hypersphere, the unit in ball. And you'll see that actually volume peaks at dimension 5. That's kind of a weird thing to think about. Like, why is it that in dimension 5, this ball, which I can just define as having norm less than 1, why does that have maximal volume? Does that have any significance in our physical reality? I'll leave that to you to think about. But notice that also when I increase the radius a little bit, now it looks like my peak is a little bit later, dimension 7 or so. So this also seems to be a function of radius. If you're feeling aggressive, you should maybe do a little bit of calculus and see if you can figure out a pattern here. All right, cool. So let's try to put these observations together. So I've just given you a formula for the n ball for various dimensions n. And I'm going to write a little function which says, well, let's look at, I think of this sort of shell of the sphere where I go the volume up until radius 0.9. And then I look at up until radius 1. And then I ask, well, how much volume is left over between that 0.9 and 1 multiple of the radius. And I'm going to see how this changes as a function of dimension. And this is really what the cursive dimensionality is all about. So in dimension 5, only 40% of the volume is between 0.9 and 1. Still quite a bit of it, but there's nothing to compare to these higher dimensions. And dimension 10 ends up being 65%. Dimension 15, it's more like 80%. By dimension 20, almost at 87 or 88%. And by dimension 25, well over 90%. So closer to almost 93% of the volume is contained in this thin shell. And what that means is that even if you think of, you have your test sample point and you look at, you assume that points are sort of distributed uniformly inside my sphere. But this is a sphere inside of my feature space, which could be, let's say, 25 dimensional. If I have points uniformly distributed in there, it's still going to be the case that 92% of the volume, and hence 92% of the points, are going to be almost the same distance away from you. So meaning distance between 0.9 and 1. So that means if there's any little noise, it's going to quickly be confused. And so I'll say the upshot of the cursive dimensionality is that if you're trying to use k-nearest neighbors, and in fact, a lot of machine learning methods in these higher dimensions, above dimension 20 or so, you can expect that some of your accuracy goes down as you start testing on more of your testing data. And all I've done here is gone ahead and given you a plot which shows how this goes and what happens in dimension 23. All right, cool. Well, you can see again that close to 100% of all the volume by dimension 40 is going to be contained in that last shell. And you, of course, can compare this. Now, what happens if you make this 0.95? And then you ask how much volume's there. It'll be less aggressive, but still something to be mindful of. All right, so that's it for basically the math content of today's lecture. I'm going to go ahead and now give you a quick survey of a part of Python that I've been sort of dancing around and using lightly. Now it's time that I go ahead and give you some of the tools for understanding the syntax and what are these objects as far as data types are concerned. So pandas, the key difference between pandas and numpy is that it allows heterogeneous arrays of data. So meaning the type of the data inside of these arrays can vary. It doesn't have to be all Boolean or all float or all string or what have you. It is still built on top of NumPy, so there's going to be a lot of close similarities between NumPy and pandas. But you want to think of them as enhanced NumPy structured arrays in which rows and columns are identified with labels instead of indices. So this is actually going to make pandas feel a lot more like a dictionary. And also, it's so much nicer to visualize data with. So let's go ahead and go through some of this. So first of all, we need the generalization of an array. And for pandas, it's called a series. Series sort of both wrap sequences of values and sequence of indices. So let's go ahead and look at this. So again, I'm going to import pandas PD. I'm going to create a PD series where I've got my my sort of list of data. And then I'm going to give some indexes here. So let's see what happens when I do this. So here I've gone ahead and wrapped this list as a panda series where I then index each element of the series using a string. In particular, it looks like a color, red, yellow, green, blue, purple. And so it gives me some summary facts about it. All right, most of these entries are floats. That's the data type corresponding to each of these indexes. Now, remember, I just wrapped, I created some data is this panda series where I've fed it a list of data values and some indexes, some indices. So if I go through and I look at, all right, just like in dictionaries, what are its values? Well, it's going to tell me. And then I ask, well, what about the index? This was what we called keys for dictionaries. And it's just going to give me some strings and tell me a little bit about their data type. And if I ask, well, what's the value associated to sort of the key or the index, yellow? Well, again, I see yellow is 0.25. So Panda series isn't so different. And as I mentioned, these kind of look like dictionaries. So you could take in, and in fact, you can take in dictionary and use values to create these indices. Let's go ahead and see through some of these examples. So again, just sort of being sure to import my pandas again, but once I've done it once, I don't need to do it again in a single notebook. So here I've got my population dictionary where I've got states along with their populations. So it looks like California is 38,332,521 people. Texas is more like 26 million. New York looks like 19. I'm not sure if these numbers are right. But either way, this is a dictionary, called it population dict. And then I can just go ahead and feed it into pandas to create a series, just like I did with like a NumPy array, Indy array. And notice that I could still do some of the slicing that I do with other sort of iterable objects. But if I, for example, say, well, I want to slice between the index California and the index New York, it's going to go ahead and include that entry along with its values. And so it's going to give me California, Texas, and New York. So in this sense, the Pandas series is ordered. And so it understands to include Texas in between California and New York, because that's how I created it. All right. So the next other bit, and this is the thing which we're really going to be using more of, these are Pandas data frames. So it's like a series object, but it can be thought of as either a generalization of an array or as a dictionary. So let's go ahead and try to build up a data frame. So again, now if I consider, let's say, California, Texas, New York, along with its area, let's say measured in square miles. So again, just as you already saw, it kind of looks like a somewhat fancy table where it puts all my indexes on one side and values on the other. But let's now go ahead and create a data frame where I use population and area. Now let's make sure we understand what population and area is. So going back briefly, population was this Pandas series created from this population dict. And then I created area, which is another Pandas series created from this dictionary. And notice that they both have similar indexes given by states. So what happens if I now create states, which is going to be a Pandas data frame where I've got, population with the population series, an area and the area series. So this is beautiful. So you can see how Pandas data frames already is much nicer to look at. And it's gone ahead and identified that there are these common indexes between these two series. And it's gone ahead and sort of appended these values associated to each of these indexes, but also understanding that each of those entries are also indexed by something, population or area, which has now been placed as the heads of our column. So let's try to manipulate this object a little bit. So again, with this sort of object-oriented mindset, when I use any of these like dot notation, I'm sort of accessing attributes of these objects. So in this case, my index, it thinks of as my states. But then I look at, you can think of this as indexing the rows. But then also if I look at the columns, gives me this list of population area, and then values, it knows to return a sort of list of lists corresponding to each of these things where the rows are indexed by my indices, which is California, Texas, New York, Florida, Illinois. So let's go ahead and create another smaller toy data frame. I'll call this data frame 1, DF1. And this is where I have A associated to 4, 5, 6, B associated to list 7, 8, 9, C, the list there. And I'm going to go ahead and tell it what I want these indices to be. And then I'm also going to do it where I've got my data frame. I'm going to pass it as a list of lists. I'm going to give the index values to be just as it is here, but also give column labels. So again, these are examples of sort of default keywords when calling this this initialize function for the Pandas data frame class. And so let's go ahead and print both of these. You'll see they're indistinguishable, which just tells you that there are many ways to create the same sort of object with similar attributes. Here is sort of done using a dictionary, where I then specified later what the indices were, and here was a list of lists where I then had to specify the index and columns later. So notice we have these two sets of labels, rows and columns. So we need to be careful how we parse through these things. So again, states, it's this nice looking thing. But now let's see how we return a column. So notice we can do this by calling the column by its name, but we've got to kind of use the fact that this sort of states, I don't want to just use a single square brackets. In fact, I need 2 square brackets because sort of the indices are actually going to be corresponding to rows. And so I then pass it the fact that I want to think of it as a column by inserting an extra set of square brackets. So states square bracket population, then looks like that. And now let's imagine I want to get 2 columns. Again, remember we created this thing with the ABC and then 1, 2, 3, but then they had the list 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I just look at the first 2 columns, I get my 4, 7, 5, 8, 6, 9. And then it has my indexes here, 1, 2, 3. All right, so how do we return rows? Well, there is a sort of special method for returning rows instead of just doing this kind of slicing that we've been talking about with some of these other data structures. And this is sometimes called the .loc or .location method. And this is used to retrieve rows in a Pandas data frame. You can also, here in this case, you're going to need to use something that's a little closer to whatever you use to index your rows. But since it knows how to sort of treat this as an ordered object, you can do this iloc, which might be called interactive locator. You can just do things like slicing. So if I do that, look at states and then go up through 0, 1, 2 entry and 0, 1 column. Yes, so I've got, well, because that stops one less, it actually just returns my single column. That's my population. Here's this. If I were to change this, let's see it add another state. So I know I was interpreting that first coordinate as rows correctly. Now, what happens if I want to turn rows across all columns? So if I do that, and again, I could do it like I did up above. Now I have this, and let's see what happens. I think also in this case it should work. Aha, so here it doesn't like that. And that's just because of the fact that in general, the way these sort of columns are going to be indexed are using sort of these labels. So in this case, we were able to get away with it, but here we're not always. So now let's see how we might use it using actually the sort of indexes. So let's imagine I list everything up through New York, and I go up through area. So this is much more human readable. You don't need to, remember exactly how these things were indexed, or even remember that this number -1 is what index you're actually going to be achieving. Here you can just go ahead and say, I want everything up to and including New York, instead of New York -1, which doesn't really make sense. And similarly with area. So this uses explicit indexing and uses the indexes that were used to create my data frame using .loc. But iloc allowed me to use these sort of integer indices. So data frames are extremely nice objects to manipulate, and they're easy to modify and append, even more so than lists. And you also get all the sort of vectorized operations that were nice in NumPy. So for example, I know I've got a column of populations for each of my states, and I've got a column for the areas of each of those states. So I might be able to create a new column with the column level density, which tells me something about the population density. And notice it understands to divide one column by the other, and it can handle all sorts of weird things. So here we can see that, even though population numbers might be comparable, the density of New York is much higher than Florida or Illinois, definitely much more dense than Texas. And all this was done in a single line, which again, knows if you know how to work with these vectorized operations where you treat columns and then you just imagine you multiply columns or divide columns, it knows you need to do it entry by entry. Now we can do the same sort of thing. All right, so let's go ahead and do our parent states.iloc 1, 2, and then let's look at it using Texas and density. And notice that it does achieve that entry, because again, we're thinking about 1 actually means 0, 1 down, and then here I'm stepping through my columns 0, 1, 2. So that's why it's iloc 1, 2. Or I could just think of the location that corresponds to these indices. Again, much more human readable. So I think if you remember, one of the nice things with NumPy is that we had all these comparison operators to extract out subarrays. Same kind of stuff works with pandas. So let's go through that. All right, so those were states. And looking at were the entries greater than 100. All right, so in these cases, they were not. So it did not return that. Go over areas greater than 180,000. Okay, cool. But then we can also use some of these built-in statistics operations, such as what's the mean, the variance, and then of course the square root of the variance, which is standard deviation. And all this is done just by simple, take my data frame dot mean, take my data frame dot standard deviation. It's going to give me all this information here. So here, what I did is you'll see how it interprets. Okay, DF1 had these column headings ABC, and then when I looked at what's the mean across all the A entries, well, let's see, 4 plus 6 plus 5 is 15 divided by 3, means the mean of the A column was 5. And the mean of the B column was 8, and the mean of the C column was 11. And in fact, all these end up having the same standard deviation, even though the mean was different. But here you can see how it's going to understand, all right, if I were to do, say, like states.mean, I'm going to go ahead and do that, states.mean. It's going to go ahead and tell me what's the mean population, the mean area, and the mean density. Cool. So two other last sort of statistical measurements. So covariance, again, sort of asks if you have two variables or two features, X and Y, well, you can always look just at the variance amongst the X values and the mean of amongst the X values. You can also do the same thing, look along the Y values and look at the, sorry, it's kind of opposite. So take my scatter plot of points with a X and Y coordinates, and then I can look at the mean of all the X values and their variance. I can look at the mean of all the Y values and its variance. But then I can ask, well, does it happen to be the case that X and Y vary in the same kind of way? So meaning that when X is above its mean, you know, like over here, is Y above its mean. And similarly, if X is below its mean, is Y below its mean, in which case you could see there might be a linear correlation or some sort of correlation between X and Y. So let's go ahead and see that in our case here. So here's states, I'm gonna look at my population, and then ask how does that covary with the area? And then how does that also correlate with the area? So this first guy here, states, how does that, what's the covariance with area? The population area, well, it ends up getting this big number. But if I look at correlation, and correlation is essentially derived using covariance and then variance of each of the variables involved, and takes a divide by 1, take a square root, end up getting some number between -1 and 1. 0.62 sort of shows there is sort of a decent correlation between area and population, which again makes sense. But you can, if you also just apply the .cov method for covariance, or the .core method to the whole data frame, it's going to go ahead and ask, how does each of these attributes covary or correlate with the other one? So obviously population and area is going to be 100% correlated with itself. There's nothing interesting there. But you can then ask, population somewhat correlates with area, negatively correlates with density, and then similarly for each of these other guys. So notice area and density tend to have a high correlation, but in a negative way. Bigger density means smaller, bigger area means smaller density, and so on and so forth. And then of course you just look at the whole data frame there again. So you always want, when you're doing some exploratory data analysis, to do some basic visualization. And the most basic instances of visualization in statistics are going to be things like histograms, scatter plots, and line graphs. So here we're going to go ahead and bring back in our example from last lecture, where we look at the iris data set, which we know has these names, which is how we end up creating our data frame out of my comma separated value sheet. That's CSV. Okay, cool. So now I brought that into memory. So now let's first look at what's the head of this data frame, which I'm just calling data. Cool. Well, I see here I've got my first four features, my only four features in the class that it belongs to, and then also with indexing the sample number. Now here's a nice way of plotting. So I can take my plot and I can ask, I'm going to do a histogram plot. Let's just pass that with kind equals histogram. I give it a title. I do iris histogram. And it very beautifully, all in one line of code, gives me an automatic binning of petal widths, sepal widths, petal lengths, it's in green, or sepal lengths, which is in blue. And these were sort of the four features, and we see that they each kind of vary, but actually together they can be used to classify what iris species it is. And we had like 100% or damn near 100% classification with k-nearest neighbors algorithm. And of course, you can fiddle with attributes of these plots, change the number of bins, change the figure size. So here you get much more fine separation data, and then you can sort of tune this to be however you like, whatever you think looks good. Okay, so you see there's more spikes. It reveals sort of finer structure in your data. Go ahead and put it back up to 75. How about 70? All right. Now we can also extract out sort of subframes. Look at all the columns with sepal width, sepal length, and we can plot a histogram of just those two features. So you can see here the comparison between sepal width and length. The width thing, these things tend to be not as wide as they are long, which makes sense, you know. We can also do a line plot, and here now it's using the index given by sample number. And you'll see that there's some trends where things here tend to have smaller petal width, petal length, and then as we jump across these classes, they increase. But sepal width doesn't. It kind of just oscillates down, and but then sepal length kind of goes up. So that was the problem with this data set, was that you couldn't linearly separate out these different attributes to get at the three different species. But nevertheless, we can do some things where we plot and see correlations between some of these variables. petal length, petal width in this case. And of course, when you have features like this, you understand that there's an obvious correlation here. And we detect that by first plotting, looking with our eyes, and then we can use some of the models that we've already talked about today, with linear regression. And here we noticed we needed to do a little bit of massaging or pre-processing of the data in order to get this to work. So if X is coming from my petal width column and Y is coming from my petal length, so here's petal length, petal width. Notice I knew how to scatter plot that without me having to do anything. But in order to do my my linear regression on here, I need to go ahead and sort of reshape X to make it look more like a column vector and give it an axis. I do all that, then able to get essentially the same plot as above. Of course, I'm using the Seaborn package, so things look slightly different. But here I now get my line of best fit. And again, remember that when we're running, we have this sort of train model predict pipeline, both sort of philosophically, but also in terms of how attributes are being treated or handled. When we create instances of these models in Python, and then we apply these methods to fit and transform these attributes. And then we can access these attributes using things like what we saw already, .coefficient 0, .intercept, and then get the equation for the line as we just saw here. And so, and of course, I hope you remember that one of the things you can do is sort of get your R² value, which gives you your sort of helps score how well this model works. And I encourage you to go ahead and look up and understand how that works in careful detail in case you forget. So here's some links. I encourage you to just start coding, and whenever you need to remember how command works, you can consult one of these references. All right, well, I look forward to seeing you all in class.